Hello and welcome to our presentation on understanding the Fourier and Laplace transforms. I am Ted Mokentine and I am here with my presentation partners Ben Stark and Brendan Zember. And we are recording this on the 22nd of April for the 2020 online math retreat. So a quick overview of what we're going to be going through here today. We're first going to talk about a little bit of an introduction to complex variables before we get into the materials to make sure that everyone understands some of the things we'll be going through. We're then going to talk about the Fourier transform and specifically look at the definition, the equation, and then two examples, a box function example and a sum of sinusoids example. We will then take a look at the Laplace transform, again specifically looking at the definition and the equation, and then going through one more example. So a very brief introduction to some complex variable terms. So Euler's formula is the first line listed there. E to the ix is equal to cosine of x plus I sine of x. And this is a very important formula in complex analysis. And specifically for our purposes today, the reason why we want to make note of it is because of the second equation. Sine of x is equal to e to the ix minus e to the ix over 2i. And the reason why we have this equation here is because this will come up in several of our calculations. So just a thing to note. The next thing we want to talk about is the Dirac delta function, which is a special function used in physics to model the density of a point mass. And that is a piecewise function which is defined to be 0 everywhere except for a value of x, and at that value of x it is defined to be infinity. And then the integral from negative infinity to infinity of that function is equal to 1. So with that out of the way, we can now get into the Fourier transform. So the Fourier transform is a function which maps the real valued functions to complex valued functions. And it can be described in two different ways. First, it can be described as a decomposition of a function into its sinusoidal components. And second, it can also be described as a way to transform a function from the time domain into the frequency domain. Now that's a lot of words right there. We're going to go through two examples that explain what these mean in depth. But before we go through any examples, we should go through what the actual transform is. So if we have a function f of t, then taking the Fourier transform of the function, we then denote that as a capital F based on the variable omega. And that is defined to be the integral from negative infinity to positive infinity of that function multiplied by e to the negative I omega t dt. Similarly, if we have the capital F of omega function, we can then take the inverse Fourier transform of that, and that is also given for you below. So for our first example, an electrical circuit has an amplitude of 0 except for a brief period of t seconds where the circuit has an amplitude of a. Write a function f of t to describe the amplitude of the circuit at time t. Then use the Fourier transform to write a function capital F of omega that represents the amplitude of the circuit at frequency omega. So to get an understanding of what this question is asking, the best thing to do is probably to draw a picture. So what we basically have is a function that has a single pulse with an amplitude a. And so if we were to draw a x-axis of time and a y-axis of amplitude, we could denote this by the picture shown there below, where the value of the function is going to be 0 everywhere except for negative capital T over 2 to positive capital T over 2, and where it is a between those two values. And this is known as the box function simply because of the fact that it looks like a box, and it comes up a lot in electrical engineering circles. So if we were to write an equation for this, then we would end up with the piecewise function there shown below. So it would be a for any absolute value of t less than capital T over 2, and it would be 0 for any absolute value of t greater than capital T over 2. So plugging that into our Fourier transform equation, we then get capital F of omega equal to the integral from negative capital T over 2 to positive capital T over 2 of a e to the negative I omega t dt. And just one thing to note, because of the fact that the function is 0 everywhere except for the value in which it is a, then the integral changes from negative infinity to positive infinity to negative t over 2 to positive t over 2. So by just simply taking this integral, we can simplify this out quite nicely, and then we can actually simplify the equation a little bit more by using that sine equation that we talked about earlier. And so all of this then ends up simplifying down to 2a over omega multiplied by sine of omega t divided by 2. Now, this is a perfectly acceptable answer for this equation. However, because of the fact that this comes up a lot in different engineering circles, engineers have actually defined a new function called the sinc function to work with what they're working with a lot easier. So by doing a little bit more algebraic manipulation, we end up simplifying this down to at times sinc of omega t divided by 2. And that would be the final answer for this situation. If you wanted to graph the function, this is what it would end up looking like. This is the sinc function for the box problem we've just gone through. So as you notice, then for any omega, the function tells us what the amplitude is at that time.
All right, so the Fourier transform, as much as it can be described as converting from a time domain to a frequency domain, a really nice byproduct of that is that when you have a sinusoid, the Fourier transform extracts out a component of the frequency of the sinusoid. And so this has a lot of applications for signal processing, where if we have a very complex signal, applying the Fourier transform will give us a nice visual and mathematical simplification of the sinusoid components of that signal. So, for example, a musical note, when it's played, it vibrates through the air at a single frequency that can be represented as just a sine or a cosine at a certain frequency. However, when several notes are played at the same time, the signal it creates is much more complex. And so, for example, we're going to take a signal that is the sum of two cosines, cosine of 2t and cosine of 4t. And so if we look at the graph for that, it's obviously not as simple of a sinusoid. It has a bit of an irregular pattern to it. It still loops every so often, but it's not as nice. So if we want to extract out the sinusoid components of the signal, we can apply the Fourier transform. So we have our function, the sum of our sinusoids, multiplied by a complex exponential. Now that complex exponential, using Euler's formula, as noted earlier, can be broken down into a cosine and a sine frequency. And so just foiling that out, we can end up with a sinusoid in the real valued function and a sinusoid in an imaginary valued function. And so using the properties of the sine function, that imaginary component is going to end up being an even function. So when we take the area under the curve for the entire function, we end up with simply 0, leaving us with the integral from negative infinity to infinity of our sum of sinusoids function times cosine of omega t, where omega is some arbitrary angle. So now, an important note about this function is that when omega is almost any angle, our function is going to be oscillating back and forth between positive values and negative values over and over. And so the sum, the area under this curve, is going to be approximately 0 for most values of omega, except for when that angle complements cosine of 2t or cosine of 4t. In that case, then we're going to end up with an infinite value of the area under this curve. And so that translates nicely to the mathematics of this. When omega is equal to 2, -2, 4, or -4, we end up with an infinite value. Everywhere else, we're 0. This should sound familiar. This is the Dirac delta function that we talked about in the beginning of this video. And so we see that the Fourier transform of the sum of sinusoids is the Dirac delta function at 2 plus the Dirac delta function at 4, lending us this nice graph where we're 0 everywhere except for at the frequency of the sinusoids that we inputted into the transform, 2 and 4.
So moving to the second type of transform we have is that we'll be focusing on for this particular presentation is the Laplace transform. It is defined as a function which maps real valued functions to complex valued functions, but it can be described in two other ways, as the decomposition of a function into its sinusoidal and exponential components, and transforming a function of time into a function of a complex frequency s. So as you may notice, the two are quite similar. The Fourier transform is denoted in contrast to the Laplace transform just below it. And the main differences are that instead of an omega, we have a letter s, which now has a complex and a real component to it, as displayed below, with sigma being the real component and omega being the imaginary. And the bounds are also different from 0 to infinity in the case of the Laplace transform. So the most common use of the Laplace transform is initial value problems, and those are specific cases of differential equations. The most useful or common occurrence of this would be with the second derivative with respect to time of some function y. So if we were trying to solve for that function y of t, it's very common to use the Laplace transforms. And in doing so, the general idea is to take the Laplace transform of each particular term in the equation. So if we are given an equation of y double prime minus 2y prime plus y equals 9t, and we have the initial conditions for y of 0 and y prime of 0, in this case, -3 and 1 respectively, these following formulas are actually calculated and established for the Laplace transform of y double prime and y prime. The main thing to note is that capital Y of s is what you are ideally solving for, because once you have that component, you can use the inverse Laplace transform and apply it to end up with the original function y of t. So moving on to an example, a calculated example of the Laplace transform, we will consider the function f of t equal to 3 sine of 10t times e to the -5t. Now, this calculation is fairly straightforward. It's inputting that function and taking the integral. So the main things to note are the use of Euler's function, or Euler's formula, and representing it in the representing the s equation in terms of the real and imaginary parts. So once we move through the calculation of that integral, we are left with the Laplace transform equaling 30 over s plus 5 squared plus 100. So for this particular function that we are given, the Laplace transform has been reduced to that exact result. So if we were to generalize this formula for e to any number value a multiplied by t times sine b of t, then the Laplace transform is simply b over s minus a quantity squared plus b squared. So with this, the applications of Fourier and Laplace transforms include signal processing and image processing, partial differential equations, combinatorics, electrical engineering, and many more. So with that, we leave with questions that you may have and the references we used.